How would we create an expression for the perimeter of this rectangle? Well, the formula is perfect. The formula is 2 times the length plus 2 times the width. What are we going to plug in for the length? Perfect. 8x squared plus 2x. And then for the width? 3x squared minus 7x. Good. It really doesn't matter which one we put where. They're kind of interchangeable in this formula. So now we're going to have to simplify it. We see parentheses. Parentheses should always scream at us, do something here first. So going left to right, this parentheses, is there anything that needs to be done inside that parentheses? No. Anything needs to be done to that parentheses? Yes, multiplying by 2. So 2 times 8x squared, 16x squared. 2 times 2x, 4x. Good. Now over to this parentheses. Again, there's nothing to do in the parentheses, but there is something to do to the parentheses. Times 2. So 2 times 3x squared, 6x squared is going to be positive, so I'm going to plus 6x squared here. 2 times negative 7x, negative 14x. Are we done? No, we're not. What do we do? Combine 16x squared with 6x squared makes 22x squared. Perfect. 4x combined with anything? Times the negative 14x. So negative 10x. And there it is. The hard part there is simplifying the formula once we get it put in. Of course, sometimes it's a little tricky remembering what the formula is, but not hard to plug the expressions into the formula itself. So let's take a look at another one that we have to simplify. Something like this. Give this one a shot in your notes quick. Where do we start? We have the parentheses, and we're going to have, there's nothing to do in those parentheses, so we do have to distribute. It's not a 7x squared, but negative 7x squared. So I'm going to leave the 9x to the 9th up front. Nothing's going to happen to that. Negative 7x squared times 3x to the 4th. Perfect. Negative 21x to the 6th. We add the powers when we're multiplying variables. Bless you. 2 plus 4 makes 6. Then we also have the negative 7x squared times 4x to the 7th. Negative 28x to the 9th. Good. Then we still have the negative 8x to the 6th on the back end. Now what? Combine. 9x to the 9th combines with negative 28x to the 9th, which is going to make negative 19. Perfect. Negative 19x to the 9th. What's next? Perfect. Negative 21x to the 6th and negative 8x to the 6th makes negative 29x to the 6th. The key to remember is when we are multiplying variables, we add the power. So when we're multiplying, x squared and x to the 4th make x to the 6th. We can multiply any variables no matter what the powers are. When we're adding or subtracting, first of all, they have to have the same power. X to the 6th only combines with other x to the 6th. And then we keep that same power of the variable. We keep the same name when we add or subtract. Any questions? Sure.
You multiply, you say we add.
when you're multiplying variables, like x to the 8th times x to the 4th, you're multiplying, but what the appearance is that you're just adding the powers. 8 plus 4 is 12. Bless you. So if we have something like 9x to the 5th times 4x to the 8th, we are still multiplying. 9 times 4 is 36. We're still multiplying that. But on the variables, when we multiply variables, the powers get added. So 5 plus 8 makes 13 is the power on the x. Remember, the reason for that, x to the 5th is 5 x's multiplied together. X to the 8th is 8 x's multiplied together. If I multiply them together, I now have 5 plus 8 or 13 x's multiplied together. So even though I'm multiplying the powers, the appearance is that the powers are being added. Any other questions? That's one that does take a while to get used to. And as I was saying, the other side of that is if I'm adding 9x to the 5th plus 4x to the 6th, can I add those? No. They have, when I add, I must have the same name. X to the 5th and x to the 6th are different. So I can only add them if they have the same name. And then if they do have the same name, I'm going to combine the 3 and the 9 to make 12, and then I keep the same name. The power stays the same. Any other questions? One of the other things we did last class was we did factoring. We had something like, oh, what do I want to put out here? Let's do 84. And I asked you to factor it. And to factor, one of the tools we used was the factor tree. What is any number? Give me one number that divides into 84. 2. If we did 84 divided by 2, we were left with 42. 2 is prime, so I'm going to circle it. 42 can be split up. What's a number that can divide into 42?
6 and 7.
So 6, if we 42 divided by 6 leaves us with 7. 6 can be split up. 7 cannot. 7's prime, so I'm going to circle it. 6 splits up into 2 times 3, or 3 times 2. Both are prime. So now my factors of 84, I write them from smallest to largest. So I have 2 times 2 times 3 times 7. Or I could write that as 2 to the power of 2 times 3 times 7. Either of those notations is perfectly fine. If my math lab, of course, asks for exponential notation or Empower notation, of course you want that one. If you did it the other way and my math lab counted it wrong, by the way, let me know and I'll change your grade for that. I accept it either way. So why were we so concerned about factoring? Well, one of the things we discussed last week was fractions. And factoring is a huge tool in dealing with fractions. For example, we could have something like 45 over 120. And we're asked to reduce that. Now, when we look at that and we want to reduce it, what we're looking for, the way we did it, is we looked for numbers that can divide both the 45 and the 120. And we did talk about divisibility rules that make that quicker. Remember, I said I always look for 10s. Can both of those be divided by 10? No. 120 can, but not 45. Second thing I usually look for is 5s. In this case, both of them can be divided by 5 because they end in either 5 or 0. 45 divided by 5 is 9. 120 divided by 5, 24. Any more 5s? No. Next, I usually go to 2s. Can they both be divided by 2? Nope, 9 can't be divided by 2. How about 3? Yes, divide by 3. 9 divided by 3 is 3. 24 divided by 3 is 8. So 3/8 is what that reduces to. One of the ways we could reduce a fraction is with our factoring. If I did the factor tree of 45, I get 3 times 3 times 5. For 120, 2 times 2 times 2 times 3 times 5. First of all, is everybody doing okay with the factor trees, getting the factors? Anybody that has questions on those? Okay. So once we can factor these out, all we're looking at reducing a fraction is canceling common factors. We divided by 5 up here. All that really was doing is canceling out a 5, a factor of 5. Dividing by 3, we just canceled out a 3, leaving us with a 3 on top. And on bottom, 2 times 2 times 2, which is 8. We don't write it out this way because most of us are good enough with whole numbers that we can just look at it and do dividing by 5 and dividing by 3. Before the night's over, though, we're going to throw some variables into our fractions where being able to factor them makes a big difference. Yes, I know. That wasn't a threat. I'm sorry. Some other things. Yeah, fantastic. Sounds so excited. Other things we did with our fractions as we ran into things like this. (58/9). This, of course, is what we called an improper fraction. Nothing wrong with it, even though we call it improper. It's just not the preferred way of having it written, at least in most cases. When we're working with them, there are times when we prefer to have it written in that form to calculate with it. We can convert improper fractions. They're considered somewhat simpler if we put them as a mixed number. A mixed number is where we have the number of whole objects with pieces left over. So how do we turn an improper fraction into a mixed number again? It's a division with a remainder. 58 divided by 9. Well, 9 goes into 58. 6.444. Right? 6 times 9 is 54. There are 4 pieces left over, so that's 6 4/9. So as a mixed number, 58/9 is 6 4/9. Now, one thing I'll warn you, punch that in your calculator, you get 6.4444. The temptation is, oh, it's 0.4, so it's 4/9. Be really careful with that. Because we might have, let's see here, 79/5. If you were to punch that in your calculator and divide that out, that is going to become 15.8. Does that mean it's 15 8/5? No, it's not. You got to do division and remainder. 79 divided by 5 is 15. 15 times 5, though, is 75. How much is left over? 4. So it's 4/5. So 79/5 becomes 15 4/5 as a mixed number. We also went the other direction. 3 1/4, which is a mixed number, and converted it into an improper fraction. 3 1/4, how am I going to make that improper? I'll have to break the 3 whole objects into pieces. So perfect, yeah, 3 times 4 tells us that's 12 pieces, plus the one that's there is 13/4. Yeah. 3 times 4, which is 12, plus the 1, added to the 1. So like 7 2/3. 7 times 3 is 21, plus the 2 is 23/3. And the denominator here is always the denominator we started out with in the mixed number, because we're dealing with fourths. Or down here we're dealing with thirds. Now in the example we just did, we dealt with powers where we had x to the 5th times x to the 7th, and we get x to the 12th. We mentioned briefly in the last couple of classes something like this. X to the 5th divided by x to the 2nd. What would we get? It is going to be x to the 3rd. It's that same concept we just talked about with our fractions. X to the 5th over x squared can be thought of as a fraction. We write them out. We've got 5 x's multiplied together for x to the 5th. X squared is 2 x's multiplied together. If we're canceling out, think of those as factors, basically. We cancel out common factors. We cancel an x. We cancel another x, and what we're left with is x to the 3rd on top. If we have y to the 17th over y to the 9th. Now basically what happened here, just like when we multiply variables with powers, the appearance is that the powers get added. When we divide variables with powers, the appearance is that the powers are subtracted. So this is going to be y to the 8th. 17 minus 9 is 8. If I have 24z to the 13th divided by 8z to the 2nd. Just like when I multiplied the counts and then also multiplied the names. I do the same thing here. 24 divided by 8, 3. Z to the 13th divided by z squared is z to the 11th. Perfect. So how about this one? 18 divided by 9 is 2. X to the 2. Good. 5 minus 3 is 2. How about this one? 36 divided by 9 is 4. Y to the 3rd divided by y to the 4th. Y to the negative 1. 3 minus 4 is negative 1. We're going to talk about that more later. Didn't know we could have negative exponents? We'll show you here. How about this one? What's it going to become? Trick question. It stays that way. X to the 7th over y to the 4th. Now we've shown this negative power here. Y to the negative 1. What does that mean? Well, let's look at real numbers. Let's look at 5 to the power of 3, which is 125, right? When we see something in math that we don't understand or doesn't make sense according to the definition, we look for patterns. So I'm going to start out with 5 to the 3rd power, which makes sense. It's just 3 5s multiplied together is 125. 5 to the 2nd power is 25. 5 to the 1st power is just 5. So if we look at our pattern, when our power is reduced by 1, our result here is divided by 5. So if we're to keep going, 5 to the power of 0 is, well, if we divide by 5, we get 1. 5 divided by 5 is 1. If we were to keep going, 5 to the negative 1, well, what's 1 divided by 5? 1/5. 5 to the negative 2, what's 1/5 divided by 5? 1/25. 5 to the negative 3, 1 over 125. You'll see a connection here. 5 to the 3rd is 125. 5 to the negative 3rd is 1 over 125. 5 to the negative 3rd is equal to the reciprocal of 5 to the 3rd. Negative powers actually mean reciprocal. Flip it over, or 1 over this. So if I tell you that, well, let's do 8 to the 4th power is 4,096. What's 8 to the negative fourth power? 1 over 4,096. It's the reciprocal of it. So if 3 to the fifth power is 243, 3 to the negative fifth power has to be 1 over 243. Perfect. So y to the negative 1 has to be 1 over y. Likewise, I had that example, x to the 7th over y to the 4th. I could leave it like that. That's just fine. If I wanted to express it without the fraction, I could do this. That's x to the 7th and y to the negative 4. Well, how did I get y to the negative 4? Because y to the negative 4 is 1 over y to the 4th. Which is what we had down here. That's something that we're going to get used to as we work through this, is switching back and forth between that. If I have 1 over z to the 7th, that's the same as having z to the negative 7th. Or likewise, if I had a to the negative 4th, that's the same as having 1 over a to the positive 4. So if I wanted to write this without any fractions, if I had x to the 5th z squared over y to the 3rd q to the 5th, I could write that without any fractions. It would be x to the 5th, y to the negative 3rd, z squared, and probably q to the negative 5th would go up front, because I should put my variables in alphabetical order. Notice the x and the z didn't change because they were already on top. The y and q were on bottom, so those became negative y to the negative 3rd and q to the negative 5th. Because they were on the bottom of a fraction, or in the denominator. The other side of that, let's say let's just write out a problem here. 48 x to the 5th, y 9th z, divided by 16 x to the 7th, y to the 7th, z to the 7th. 16 divided by 3, or 48 divided by 16 is 3. Make my tongue work here. X to the 5th divided by x to the 7th is x to the 5 minus 7, negative 2. Y to the 9th divided by y to the 7th, positive 2. 9 minus 7 is positive 2. And z to the negative 6. Remember, this is z to the 1. So 1 minus 7 makes negative 6. I could leave it like that. That would be just fine. My math lab, though, will often ask you write it with only positive exponents. The 3, of course, doesn't have an exponent. X to the negative 2, make it positive. I put it in the denominator. It becomes just x to the 2nd. Y squared, where's that going to go? On top. It's got a positive exponent already. Positive power stays on top. Z to the negative 6th. Since it's negative, it's going to go on bottom and become z to the 6th. So let's say I have 5 a to the 4th, b to the negative 9th, c to the negative 3rd, d to the 5th. And I want to write that using only positive powers, only positive exponents. How am I going to write it? Well, the number, of course, goes on top. That's 5. A to the 4th, top or bottom? Top. It's already a positive power. B to the negative 9th? Bottom. It's going to be b to the 9th on bottom. C to the negative 3rd? Bottom. C to the 3rd. And the d to the 5th? Top. D to the 5th. Just like that. something like this. Now the 1/7 is already a fraction. I'm going to write it like that. A to the negative 2, where's that going to go? It's going to go, it's a negative power, so it's going on bottom. It's going to be A to the 2. B to the 8th is going to go on top. Now I'm going to replace the 1 with just B to the 8th. I don't need the 1 there. I don't need 1 B to the 8th. I just need B to the 8th. 1 B to the 8th and B to the 8th are the same. Just like 1 inch and an inch are the same thing. If I had the 1 in front, it wouldn't be wrong. It's just not necessary. And then the C goes where? Bottom, C to the 5th. Questions? Okay. Other rules of our exponents that we're going to deal with. We've seen this a little bit. We're just making sure to remember. X to the 3rd to the 4th power is going to become, careful, x to the 3rd, of course, is 3 x's multiplied together. And to the 4th power means we're doing that 4 times. So yeah, we end up with a total of 12 x's there. So x to the 12th. When we have an exponent taken to another power, we multiply the powers. 3 times 4 gives us 12. So x to the 12th. Y to the 8th to the power of 5 would be y to the 40th. 8 times 5 would be 40. Z to the 7th to the power of 3 is going to be Z to the 21st. Perfect. How about 5x to the 5th, y to the 9th, z squared to the power of 6. Is that going to become 30? Say no. That is still 5 to the power of 6, which is, careful, the 5 to the power of 6 is going to be 15,625, right? So the number, the count, still gets taken to the power of 6 in this case. So we still have to do that. Now, x to the 5th to the power of 6 is going to become x to the 30. Y to the 9th to the power of 6 is going to be y to the 54th. 9 times 6 is 54. Z to the 12th. Very good. So how about this? 3a b to the 3rd over c to the 5th d to the power of 4. Now the first thing we should always do is look and see if there's anything that can be done inside the parentheses. And right now there's not. So now each piece in the parentheses has to be taken to the power of 4. What is 3 to the power of 4? That's 3 times 3 times 3 times 3, which is 81.
81.
Now, A, what power is on the A here? 1. If it's not written, it's implied that it's a power of 1. So A to the 1st to the power of 4 is going to be A to the 4th. B to the 3rd to the power of 4? B to the 12th. C to the 4th to the power of 4? C to the 20th. And D to the 4th. That's D to the 1. 1 times 4 is 4. Not so bad so far? Okay. Now, once again, we should look inside the parentheses to make sure there's nothing we can do. And here there is not. We have that negative 3 out there, though, that's kind of pesky. A negative power means what? Means reciprocal. That negative means I have to flip this fraction over. So once I flip the fraction over, the negative's gone. What's left? We still have that power of 3 out there. But now we can just take, now it's a positive power of 3. We've done the reciprocal. We can just take each piece to the power of 3. So y to the third to the power of 3 is y to the ninth. 2 to the power of 3. Careful. 2 times 2 times 2. 8. There we go. Y to the fifth to the power of 3. Or x to the fifth to the power of 3, I should say. X to the 15th. And z to the 6th. Perfect. So on this one, where would we start? Careful. See, switching. You see the negative power. You want to take that reciprocal right away. But we always have to ask if there's anything we can do inside the parentheses. And we do have z to the 6th and z to the 4th, which is going to reduce to z squared. So we reduce inside the parentheses first if we can. Now we can do, there's nothing more we can do in the parentheses, so now we can do that power of negative 2. 4, the negative means we're going to flip it over. And now it's to the power of positive 2. So now we take each piece. X to the 4th to the power of 2. X to the 8th. 4 to the power of 2. 16. 4 squared is 4 times 4 is 16. Y to the 10th. 5 times 2 is 10. And z to the 4th. 2 times 2 is 4. And there we go. So in your notes, try that one. Where do we start? Do what we can inside first. And there's two things we can combine inside there. Excuse me. We have the 21 and 7 combined to make 3. Now the x to the 9th has nothing to change it. The y to the 4th has nothing to change it. The z's, however, z to the 2nd, z to the 5th. I could make it z to the negative 3 on top or z to the 3rd on bottom. Generally, I'm going to try to keep them in positive powers if I can. I want to pause there. Questions on where this z to the 3rd came from? That'd be negative 3, yep. Yes, z to the negative 3 would be on top, so we want it positive, so we're going to put it on bottom. Z to the negative 3 means 1 over z to the 3rd, so we put it on bottom. Now this is still to the power of negative 3 up here. So now we got to deal with that. What's that going to do? Flip it. Y to the 4th, z to the 3rd is now on top over 3, x to the 9th. And now it's still to the power of 3. So now what? Okay, so y to the 12th, z to the 9th over 3 to the 3rd power becomes 27. 3 times 3 times 3. X to the 27th. So y to the 12th, z to the 9th over 27x to the 27th. That one's a mouthful. It can be frustrating, can't it? Let's give you one a little simpler. Try that one quick. So 5 to the 5th power is 3,125. B to the 10th. D to the 40th. Good. 8 times 5 is 40. How many of you had that one right? Okay. How many are really confused and need to see more examples? Okay. Let's do another one or two. Try this one then, quick. Okay, let's take a look at this then. What do we do first? The x's, right? So this is going to be 7. Where's the x going to end up? X to the 3rd divided by x to the 2nd is just x. And it's positive, so it's going to stay on top. Nothing else changes. Y to the 4th doesn't change. The z doesn't change. Now the power of 3. Do we flip it over? No, why not? It's a positive 3, so we don't have to do a reciprocal. Then what? 7 to the 3rd, of course, is 343. X to the 3rd, z to the 3rd over y to the 12th. Y to the 12. 4 times 3 makes 12. Perfect.
Okay, so when you're doing the x's,
Yep.
why don't, oh, because it is 1.
3 minus 2 is 1, so it's x to the 1. Since it's positive, it stays on top.
Okay. I'm sorry.
Okay. It can be quite a adventure. I admit to that. How about this? 3/4, the power of 5. Our definition of a power means, of course, this is 3/4 times 3/4 times 3/4 times 3/4 times 3/4. 5 3/4 multiplied together. Well, when we multiply the numerators, the counts. 3 times 3 times 3 times 3 times 3. That's just 3 to the 5th power, otherwise known as 243. On bottom, we're going to multiply the denominators, the names. 4 times 4 times 4 times 4 times 4 is just 4 to the 5th, otherwise known as 1,024. So if I wanted to find the power of a fraction, let's say I had 7/8 to the 3rd power. All I really have to do is do 7 to the 3rd power over 8 to the 3rd power. As we saw here, 3/4 to the 5th became 3 to the 5th over 4 to the 5th. The same happens with any fraction. I can take the numerator and the denominator, each to that power. So, of course, 7 to the 3rd is 243. Or no, 343, I should say. 8 to the 3rd is 512. So if I have 1/2 to the power of 9. So we 1 to the power of 9 over 2 to the power of 9. What's 1 to the power of 9? 1. What's 1 to any power? 1. 2 to the 9th is 512. So it's 1 over 512. Any questions? So if I do 5/8 to the power of 4, do that in your notes quick. So I'm going to do 5 to the power of 4 over 8 to the power of 4. What is 5 to the power of 4? 625. 8 to the power of 4? 4,096. Good. And that's it. Can that be reduced?
No.
No? You already tried. Do you know why it can't be reduced?
Because there's not, because the 625 possibly.
Well, 625 can be divided by 5, 25, 125. 4,096 can be divided by 2, 4, 8, 16. What else? 32, 64, 1,024, 2,048. But the key is right here, could 5/8 be reduced? No. And remember, we talked about reducing a fraction is about canceling common factors. If we had 6/8, this is 2 times 3 over 2 times 2 times 2. We could reduce that because they have a common factor of a 2 that we can divide out, giving us 3 over 4. 5/8 is 5 over 2 times 2 times 2. There's nothing to cancel out. No matter how many times we repeat a 5, and when we take it to a power, we're just repeating that 5 over and over again. Is it ever going to cancel with a 2? No. And our 3 2's, no matter how many times we repeat the 3 2's, is it ever going to cancel with a 5? No. So as long as it is reduced before we do the exponent, it cannot be reduced after. So if I have something like 12/15 to the power of 3. The first thing I should do is the 12/15 can both be reduced by 3, giving me 4/5 now to the power of 3. Now, since 4/5 cannot be reduced, once I take it to the power of 3, it will not be able to be reduced. So 4 to the 3rd is 64. 5 to the 3rd is 125. Cannot be reduced. It is time for our break, so let's go ahead and end the first hour. We'll come back at 4:29.